So let's take a look at iterated integrals. Now in the previous video we looked at how to use Riemann sums to estimate double integrals, or the value of double integrals. But in this video we'll actually look at how to evaluate those double integrals. So what are iterated integrals? So let's say we have the integral, or the double integral here. The outer one is from c to d, the inner one is from a to b, of some multivariable function f of x comma y, and then we have dx dy. So dx is associated with the inside integral, so we're going to solve this one first, and then we can solve the outer one last. So iterated integrals basically help us divide the double integral into two individual integrals so that we can solve them one by one. So let's say for number 1 we have the double integral, the outer one's from 1 to 3 and the inner one is from 0 to 1, of the multivariable function 1 plus 4 times x times y of dx times dy. So with iterated integrals we have to break this up into two separate integrals. So the first one we're going to solve is the inside one, so the inside integral, and we're going to notice we're going to integrate with respect to x. So if I go ahead and rewrite the inside integral, we have the integral from 0 to 1 of 1 plus 4xy dx. Now if we're integrating with respect to x, this means that x is going to be the variable, everything that's y is going to be a constant. So the integral of 1 is just x plus the integral of 4xy. So the integral of x is going to be x squared over 2, obviously. 4 and y are both constants, so we have 4 times x squared over 2 and then times y. So 4 over 2 is 2. So then it'll simplify to x plus 2x squared y. Now since our bounds are from 0 to 1, we're going to evaluate it from the x values of 0 to 1. So realize we're only going to plug this in for x, not for y. So if we go ahead and plug in 1 for x, we will get 1 plus 2 times 1 squared, which is 1, or times 2 times y. So 1 plus 2y, and then minus, when I plug in 0, so then we get x for 0, we get 0 plus 2 times 0 squared is 0 times y, so that's also 0. So then we get 1 plus 2y. So now that we have solved the inside integral, now what we can do is solve the outside integral. So what we're going to do is put 1 plus 2y inside the outer integral. So we're going to take the integral from 1 to 3 of 1 plus 2y dy. So notice we're integrating with respect to y. So the integral of 1 is going to be simply y, and we have plus the integral of 2y, which is y squared. We're going to evaluate that from 1 to 3. Now remember, since we integrated with respect to y, the bounds are in terms of y. So we're going to plug in 3 for y and also 1 for y. So when I plug in 3 for y, we'll get 3 plus 3 squared, which is 9. And then minus when I plug in 1. So then 1 plus 1 squared, which is 1. 3 plus 9 is 12, and 1 plus 1 is 2. So 12 minus 2 gives us an answer of 10. So that is how you evaluate the iterated integral. So let's say for number 2 we have the integral from 0 to 2 of the integral from 0 to pi over 2 of x times sine of y times dy dx. So the very first thing we have to do is solve the inside integral. And notice since there's dy, we have to integrate with respect to y this time. So if I go ahead and rewrite the integral from 0 to pi over 2, once again we're rewriting the inside integral. Once again we are rewriting the inside integral here of x times sine of y dy. So now, since we're integrating with respect to y, y is going to be the variable, x is a constant. So if x is a constant, I can basically take that outside of the integral and rewrite it as x times the integral of sine of y dy. Because the integral of sine of y is going to be negative cosine of y. So we have negative x times cosine of y. Now we're going to evaluate from the bounds 0 to pi over 2. And remember, since we integrated with respect to y, we're going to plug these in to the y variable. So if I plug in pi over 2, we get negative x times cosine of pi over 2 minus, when I plug in 0, a negative x times cosine of 0. Now since this is a negative, double negative, we can make it a positive. Now cosine of pi over 2 is 0, so that's basically cancels it. And cosine of 0 is 1, and 1 times x is x. So we're left with x. So now we can go ahead and put that under the outer integral. So we have the integral from 0 to 2 of x dx. Now the integral of x is obviously just x squared over 2. If we integrate that from the x bounds of 0 to 2, we get 2 squared, which is 4, so 4 over 2 minus, when I plug in 0, we get 0 over 2, which is 0, so 4 over 2 is 2. So for number 3, we have the integral from 1 to 4 of the integral from 1 to 2 of x over y plus y over x dy dx. And so if I rewrite that inside function, or the inside integral here, we get the integral from 1 to 2 of x over y plus y over x dy. And so we're going to integrate with respect to y. So y is going to be the variable, x will be the constant. Now for the integral of x over y, since x is a constant, I can rewrite it as x times 1 over y. Now the integral of 1 over y is just the natural log of the absolute value of y. So we have x times the natural log of absolute value of y, and the integral of y over x. Now 1 over x is going to be a constant, and then we have 1 over x times y. So if we're going to integrate y, we can rewrite it as 1 over x times y squared over 2. So then we get y squared over 2x. So I can rewrite it as x ln absolute value of y plus y squared over 2x. And so we're going to go ahead and evaluate that from 1 to 2. And remember, we are integrating with respect to y, so these are going to be the y bounds. So I'm going to plug these values in for y. Now if I plug in 2 for y, we'll get x times the natural log of 2 plus 2 squared, which is 4, over 2x. And then minus, when I plug in 1, so I'll get x times the natural log of 1. Now remember, the natural log of 1 is 0, so that cancels. And we get plus 1 squared, which is 1 over 2x. So if I rewrite it, we'll get x times the natural log of 2 plus 4 over 2x. And then we have a negative here, so minus 1 over 2x. And if I rewrite that one more time, simplify, we get x times the natural log of 2 plus 4 minus 1 is 3 over 2x. So now that we have solved the inner integral, we can go ahead and put it inside the outer integral. So now the integral from 1 to 4 of x times the natural log of 2 plus 3 over 2x dx. So now we're going to integrate with respect to x. So remember, natural log of 2 is basically a constant. So x times a constant, the integral is just going to be x squared over 2 times that constant, so natural log of 2, and then plus the integral of 3 over 2x. Now 3 over 2x can also be written as 3 halves times 1 over x. Since 3 halves is a constant, we can take that outside the integral. So we have 3 halves times the integral of 1 over x. Now the integral of 1 over x is obviously just 3 halves times the natural log of the absolute value of x. So we can rewrite it as x squared over 2 ln 2 plus 3 halves ln absolute value of x. So we're going to go ahead and evaluate that from the x values of 1 to 4. So if I plug in 4, we get 4 squared 16 over 2, which is 8. So 8 times the natural log of 2 plus 3 halves times the natural log of 4 minus, when I plug in 1, we'll get 1 half natural log of 2 plus 3 halves natural log of 1. Natural log of 1 is 0, so that cancels. So if I rewrite it, we get 8 times the natural log of 2 plus 3 halves times the natural log of 4 minus 1 half times the natural log of 2. Now I'm going to go ahead and find a way to combine all three of these together. So I'm going to start by rewriting natural log of 4 as natural log of 2 squared. And I'm going to rewrite the 8 in front of the natural log of 2 as 16 over 2, so we can get common denominators here. Now, with using properties of logs, we can go ahead and take that exponent and multiply it up front. So then I can rewrite it. Instead of 3 over 2, we get 3 over 2 times 2, so 6 over 2 times the natural log of 2. If I can rewrite that, 6 over 2 times the natural log of 2. So then, since they all have the same natural logs, we can go ahead and just add and subtract the fractions. So 16 over 2 plus 6 over 2 is 22 over 2, and 22 over 2 minus 1 over 2 is 21 over 2. So 21 over 2, natural log of 2 is the final answer. So now for number 4, we have the integral from 0 to 2 and the integral from 0 to 1 of 2x plus y to the 8th power dx dy. So we go ahead and rewrite the inside integral first. Integral from 0 to 1 of 2x plus y to the 8th times dx. Now notice we have an inside multivariable function raised to a power. So in this case, the best thing to do is u substitution. So if I make u equal to 2x plus y, du will equal to the derivative of 2x plus y, but this time we're only deriving with respect to x, so y is treated as a constant. So the derivative of y is 0 then, and the derivative of 2x is just 2 dx. And so if I solve for dx, dx equals du over 2. If I go ahead and plug that all into the integral here and replace 2x plus y with u, we'll get the integral from 0 to 1 of u to the 8th times dx, which is equal to du over 2. Now this 1/2 is a constant, so we can go outside the integral. So we'll get 1/2 times the integral from 0 to 1 of u to the 8th du. Now the integral of u to the 8th is u to the 9th over 9th. We do have a 1/2 out front, so then we get u to the 9th over 18. We can go ahead and replace the u with 2x plus y. We have 2x plus y all to the 9th power over 18. And we're going to have to evaluate that from 0 to 1. And remember, we're evaluating in terms of x. So I'm going to plug those in for the x values, or for the x variables. So if I plug in 1 for x, we'll get 2 plus y to the 9th over 18, minus, when I plug in 0, we'll just get y to the 9th over 18. So now that I've found the inside integral, I can go ahead and put it in the outer integral. So we have the outer integral from 0 to 2 of this entire function dy. Now we're going to integrate with respect to y. So notice we have an inside function raised to a power. So once again, in order to evaluate or to integrate this, we must use u substitution again. So if u equals 2 plus y, then du, now we're going to derive with respect to y. So du is going to equal just simply 1 times dy, or just dy. So when I do u substitution here, we'll get the integral of 2 plus y to the 9th. I'm just going to go ahead and rewrite just this integral here over 18. So when I do u substitution here, I'm just going to replace 2 plus y with u, so we get the integral from 0 to 2 of u to the 9th over 18. And then we have dy, which is equal to du. Now 1 over 18 is a constant, so we can say 1 over 18 times the integral of u to the 9th du. And so the integral of u to the 9th is just u to the 10th over 10. Then we can multiply that by 1 over 18. So then we'll get u to the 10th over 180. Now u originally we said was equal to 2 plus y. So we get 2 plus y to the 10th over 180. So that is going to be the integral of just this portion. So now let's go ahead and find the integral of y to the 9th over 18. Now I can obviously rewrite it as 1 over 18 times y to the 9th. Since 1 over 18 is a constant, that can go outside the integral. And so the integral of y to the 9th is just y to the 10th over 10. We can multiply that by the constant. And so then we'll get y to the 10th over 180. So we have minus, so I can put minus and then the integral of this, which we found to be y to the 10th over 180. I can go ahead and combine the fractions together. So we'll get 2 plus y to the 10th minus y to the 10th over 180. And now we're going to evaluate from the bounds of 0 to 2. Remember, these are the y bounds. So if I go ahead and start off by plugging in 2 for y, we'll get 2 plus 2, which is 4. So 4 to the 10th minus 2 to the 10th. Now I apologize, that kind of looks like a 20. I'll change that to look like a 10 here. So we have 4 to the 10th minus 2 to the 10th over 180 minus, when I plug in 0 for y, so then we'll get 2 plus 0, which is 2, so 2 to the 10th minus, now 0 to the 10th is just 0 over 180. Now since these both do have the common denominator of 180, I can go ahead and rewrite the fraction as 4 to the 10th minus 2 to the 10th. Then we have a minus another 2 to the 10th, all over 180. So when you plug this into your calculator, you should get around 5,814.044 repeating. And so in a fraction, or in fraction form, that is going to be exactly 261,632 over 45. So now for number 5, we have the integral from 0 to natural log of 2 of the integral from 0 to natural log of 5 of e to the 2x minus y dx dy. So first step, obviously go ahead and rewrite that inside integral. So from 0 to the natural log of 5 times, or of e to the 2x minus y times dx. And so since we have e raised to some power here, let's go ahead and use u substitution. So let's go ahead and make u equal to 2x minus y. So then du, remember we're going to derive with respect to x, so y is treated as a constant. So du is going to be 2 dx, because the derivative of 2x is 2 and derivative of y is 0. So if we solve for dx, dx is going to be du over 2. So now if I go ahead and use u substitution, we have this integral from 0 to natural log of 5. Now 2x minus y, we said that was u, so we have e to the u times dx, which is equal to du over 2. We have du over 2. Now 1/2 is going to be a constant. We can take that outside the integral. So we get 1/2 times the integral of e to the u. And the integral of e to the u is obviously just e to the u. So we get 1/2 e to the u. And u, obviously we can replace that back with 2x minus y. So we get 1/2 e to the 2x minus y. And we're going to go ahead and evaluate it from our bounds of 0 to natural log of 5. Remember, these are x bounds because we were integrating with respect to x. So if I go ahead and plug those in for x, we'll get 1/2 times e to the 2 times the natural log of 5 minus y minus, when I plug in 0, we get 1/2 e to the 2 times 0 is 0 minus y, negative y. So then I can go ahead and factor out the 1/2. So we'll get 1/2 times e to the 2 times the natural log of 5 minus y minus e to the negative y. So now that we have found the integral of the inside function, we can now find the integral of the outside function. Realize that 1/2 is a constant, so I can put that outside of the integral. So we get the integral from 0 to the natural log of 2 this time, times dy. And so when integrating with respect to y, we have e to some function. So once again, let's use u substitution to evaluate this specific integral. So if I rewrite the integral of e to the 2 ln 5 minus y, let's go ahead and just integrate using u substitution. So if u equals 2 times the natural log of 5 minus y, and so du, we're going to derive with respect to y this time. So the derivative of 2 ln 5 is just a constant, so it's 0. And derivative of negative y is negative 1. So we have du equals negative 1 times dy, or negative dy. So then dy just equals negative du. So if I go ahead and substitute it back into the integral, we get the integral of e to the u times dy, which is negative du. I can take the negative outside the integral. Integral of e to the u is e to the u. So we have negative e to the u, and u is 2 ln 5 minus y. So now let's go ahead and find the integral of negative e to the negative y. Now obviously the integral of negative e to the negative y is just going to be positive e to the negative y. We have plus e to the negative y. Don't forget we do have a 1/2 out front as a constant. And then we're going to evaluate the integral from 0 to the natural log of 2. So when I plug that in for y, we get 1/2 times negative e to the 2 times the natural log of 5 minus the natural log of 2 plus e to the negative natural log of 2 minus, when I plug in 0, we'll get 1/2 times negative e to the 2 ln 5 minus 0 plus e to the negative 0, which is e to the 0, which is 1. Now if I were to simplify and rewrite, we get 1/2 times negative e. Now using properties of log, I can bring that 2 up front. So we get 2 ln, or we get ln to the 5 squared. So 5 squared would be 25. So ln of 25 minus ln of 2 plus, now I can go ahead and also bring that negative out front, or to up to the top. So we get plus e to the ln of 2 to the negative first power. Then minus 1/2 times, once again I can do the same thing here, bring that 2 up top. We get negative e to the ln of 5 squared, or in other words 25, and then plus 1. So now when we have two natural logs being subtracted, we basically divide what's inside the natural logs. So we get 1/2 times negative e to the ln of 25 over 2 plus, we have e to the ln of 2 to the negative first is basically 1/2. Now minus 1/2. Once again, I'll just rewrite it again. ln 25 and plus 1. Now notice that e to the ln's will cancel. So then we're left with 1/2 times negative 25 over 2 plus 1/2 minus 1/2 times negative 25 plus 1. Now negative 25 over 2 plus 1 over 2 is negative 24 over 2. Negative 24 over 2 is negative 12. So we get negative 12 times 1/2, which gives us negative 6. So negative 6 minus 1/2 times negative 25 plus 1 is negative 24. And we get negative 6 minus 1/2 times negative 24 is negative 12. Two negatives make a positive, so negative 6 plus 12 will give us a final answer of 6.